Right, this is a re-recording of the last lecture of Friday the 15th of May. The topic was iterated function systems, and part of the idea was to not only go through the work but also give you an idea of how you should be reading the work. So let's start. Scientists have discovered that complex visual images can arise unexpectedly from simple computational processes. So a very simple a program can generate really interesting ideas. With standard random, standard draw, and standard I/O, we can easily study the behavior of such systems. And we'll do that, but we won't be using standard I/O, array I/O, because we haven't dealt with that. And we don't really need it. We'll learn about something else. So the first topic that I talk about is the Sierpinski, spelled incorrectly as Sierpinski, but Sierpinski triangle. So this is a fascinating geometrical construction that comes up again and again in different processes in computer science. So this is the process we'll consider today. Start by plotting a point at one of the vertices of a given equilateral triangle. Then pick, okay, right, so we start at one point of a triangle, like 0, 0 down here. Then pick one of the three vertices at random and plot a new point halfway between the point just plotted and that vertex. Right. So we start at here, let's say this point, and we plot it, and then we pick a random other vertex. So either 1 or 2. This is vertex 0. So let's say we pick 1, we plot the midway point. So now we're going to plot this point and then repeat the process. Pick a random vertex, 0, 1 or 2, and let's say we pick 1 again, then that's halfway between the current point and the new random vertex. So we plot that point and then repeat. Randomly pick this one, and that's the midpoint. We plot it, randomly pick that one, and that's the midway. We plot it. Now we randomly pick 0, and that's the midway, and we plot that, and so on and on and on. What do they say? Continue performing the same operation. Well, it seems like we're going to get a lot of random points inside the triangle. Each time we are picking a random vertex, since we're making a random choice, the set of points should have some of the characteristic of random points. And that does seem to be the case of the first few iterations. Yeah, these points seem pretty random, but there's a surprise waiting for us. So then they go on and they give a lot of code. And when you see code like this, it's a good idea to read through it and make sure you understand what they're doing, really understand what's going on here. So they've got a CX and a CY. Those are probably for the corners. And their coordinates 0, 0, so that's that point, 1, 0, so that's the third vertex, and 0.5866. So yeah, those are the coordinates of a equilateral triangle. I think there's a square root missing here. This copy of the book may not be perfect. Okay. And I say x is 0, y is 0, so that's the starting point. And then I repeat t times r is standard random.uniform 3. So that'll return an integer that's either 0, 1 or 2. We looked at that last time. And they calculate the midpoint, which is simply the average of the current point x and the x coordinate of this random vertex r. So we calculate the midpoint like that. Midpoint is just average. And the same for the y. And then they plot that point. Okay, so this is repeated t times. So I think I understand this code, but that is not enough. I really want to play around with it. I want to modify these coordinates, and maybe I want to modify whether it's the midway point or a point that's 1/3 of the way, stuff like that. So I'm going to write this code, and that'll give me good practice in writing programs as well. And it's not taking that long. So let's say class, oops, I'm going to bring this to the front, Sierpinski. And I set up the project so that we have standard draw available. Main function. Let's start by creating a canvas. Set canvas size. I guess I'll make it 500, 500. Seems fine. I'm not going to set the x and y coordinates because this is clearly going from 0 to 1. In fact, I will set the x and the y coordinates because they'll be right on the edge 0 and right on the edge 1, and I want to have a little border. So I'm going to say change the coordinates, set x scale, and I want it to go from minus 0.1, that's just to the left of 0, to 1.1, that's just to the right of 1, and the same for the y scale. Right, and then I'm going to repeat this code that they have. So they've got two arrays, which are the corners of the triangle. Let's do that as well. Cx 0 and 1. There was one in the middle, 0.500. And cy was 0.0, 1.0, and that was 866. Good. 0.866. And then they repeat it for t times. T, small t 0 up to big T, T++. And of course Eclipse will complain because we haven't defined big T, but I will set it right here. I'm going to say big T equals 100. Let's see what that does. Then I say pick a random vertex, calculate the midpoint. Oh, we've got to have a current point, x and y. Okay, right. So let's just not forget about that. X is 0, y is 0. So pick a random vertex. R is, I wonder why they call it R. I will call it V. Standard random dot, and we talked about all these different routines, or most of them, some of them, and uniform n returns an integer 0 to n minus 1. So we always used to do that with math.random and manipulating it, but now things are becoming a little easier. And I'm going to calculate the midpoint. X becomes x plus that coordinate corner of vertex number v divided by 2. Now in the textbook they had 2.0. So that's definitely a double. And if this were an integer, it would force the whole thing to be a double, which is what I want. But x is already a double, so adding x to cx, which is also a double, is a double, and I don't really need a double in the second part as well, so 2 is fine. That's something you should know and be comfortable with, thinking about what is a double, is this going to work right, and I've got to plot the point, point, I think, yes, x, y, that's done. Okay, and at the end I want to show it, standard raw.show. Okay, let's see if this works. I haven't run this apart from in the lecture, so let's see how this works. Ooh, I can see faint dots. I'm not sure if they show up on the video, but I will definitely make the pen radius a little bigger, 0.05. Let's just see if that works. Way too big, about 10 times too big, I'd say. 0.5. Okay, I'm happy with that. So a lot of random points. Let's run it again, and we don't want the same pattern of random points. I'll leave this here so we can compare. Let me just find the other one. Right, so the points are different, but I can't really see any pattern. But I will if I make t big enough. So if I make t 10,000, I think we should see a pattern emerging. Okay, right. Now, is it done? No, it's still adding a few points, but it's very difficult to see when this process is done. So it's almost always a good idea in these cases to add system out done at the end. Okay, right, let's run again. Last time. Right, and what we have here is called the Sierpinski triangle. If we repeat this procedure enough, we will get this funny triangle shape, which has, it's a big triangle, and it's got its middle removed, forming 3 smaller triangles, and each of them have the same pattern. If you just look at the top one, we take out the middle, and now we get 3 smaller sub-triangles. And then we repeat that, and that's repeated for all of them. So this is an example of what is called a fractal, which is why it's called iterated fractal systems. We just start with one point and we transform it in a certain way, and we get the Sierpinski triangle. Now, I should be moving on in the book, but since we have a little more time in this recording, I want to fool around a little bit. I'm going to divide by 3. Just want to see what happens. It's not illegal to play around. Okay, right. So, in the big triangles, I guess, sits around here. But now it forms, still looks like Sierpinski triangles, but disjointed. Okay, what if we divide by something like 1.9? 1.9, which is smaller than 2. Okay, so we can see here that I've now got bigger numbers to work with. I'm a little outside the triangle. It still looks like Sierpinski, but it's a little dirtier. So the Sierpinski triangle arises in all sorts of situations, but there's more to it than that. They talk about what the code does, all of the code. So the question is this a random process? Well, definitely how we drew the triangle was a random process, but we always end up with something that looks very close to this. So it is an example of where some pattern emerges from from what seems to us to be a random process. Now here is a second example called the Barnsley fern. And this is going to do the same thing, except the formula is a little more complicated. Before, we always picked a random point and we transformed x based on that. And the random point, all 3 points had a probability of 1/3 to be chosen. But this time, we changed the probabilities. There are 4 ways to transform the current point, and these are the formulas for those 4 ways, and they don't have the same probability. This first transformation has a probability of 1%, and then the second one has a probability of 85%. We're going to do that most of the time. And then the second point is 7%, third point is 7%, and the fourth point, last point, is also 7%. So we can really write the same code for this, and let's do it because we can. I'm going to create a new class that I'll call Barnsley. I don't know where Barnsley is, somewhere in England, I guess. And I'm going to copy the code for Sierpinski because it's somewhat the same. So I'm going to copy all that code in here. And I'm also going to make my console a little smaller because I don't need to see anything except done. This time we don't need the corner vertices. They can go. We still have a random choice, but now it's between 4 options. 4. And instead of transforming x and y like this, we're going to transform it in different ways based on the value of v, which, oh, but we can't do that, can we? See, I was going to do a switch here, say case 0, and transform x and y. In fact, let's write this because we are going to use it. I just got to look up those transformations, and I'll put them on the side here. So x becomes 0.5 0.5, and y becomes 0.16 times y. Just to show you that I'm not making this up, so I'm getting this from the textbook. Case 0, or the first case, x changes to 0.5, and that's a typo. That should be a y, surely. Y update. Y changes to 0.16 of y. Okay, right. So, and then we break, and then there is also a case 1, the second case. I'm just going to put it on the side, and this time it's x equals 0.85 times x. I'm going to fill in all these transformations and speed up the video a little bit. Right. So I have filled in all the code for the 4 cases, but there is a small issue that I realized just before I started writing the switch, and that is that v is chosen from 0 to 3, but each with equal probability. And the textbook said that the probability for these 4 choices are not the same. They're not all 25%. The first probability or case is really unlikely. So I have to update my technique for choosing a random case. We did look at how to do that. There is a routine in standard random called discrete. It takes a double array of probabilities, and it returns an index into this array. So if this array has 4 items, slots, members, then it will return 0, 1, 2, or 3 based on the probabilities in the array. So let's use that. So I'm going to create a new double array, and it's going to contain 0.01, that's 1%, 0.85, 0.7%, and 7%. And so it's going to choose 0, 1, 2, or 3, but with these probabilities. They add up to 1, but in fact they don't really have to. I could have written this, I think. In fact, let's write it and see if it works. And it will either produce an error and tell us that it should add up to 1, and then I'll fix it, or this should be correct. There is still one other small problem with this program, but we'll get to that in a second. So I'm going to run that. Oh, and it complained. Let's see what the mistake was. Sum of arrays not equal to, okay, so they have to add up to 1. My mistake. But luckily I can undo. There we go. Click and run. And now we almost see the Barnsley fern. Okay, right. But it's not very nice looking. You can't clearly see what's going on, and that's because I've made a fundamental mistake. And if you'd done this as I have, you'd have seen that your fern does not look, I'll just skip over that, anything like the Barnsley fern in the textbook. There are 2 reasons for that. One of them is that there is another typo in this book. So this first edition just had a small typo. There's supposed to be a minus sign over there, in addition to that being a y. So we can see here that there actually should be a minus sign in front of the 15. So let's fix that. This should be minus. And I think the others are all correct. Yes, I can see that they are. And the other mistake is my mistake. X and Y are updated based on the transformation of the current point. So X becomes 0.85 times the old X plus 0.040 times the old Y plus this value. and y should become 0.04 of the old x, 0.85 of the old y, plus that value. But if I change x here, I've lost the old value of x. I've replaced it with this new value of x, and it's no use trying to multiply this new value by 0.04. This is supposed to be the old x. So before I start this procedure, I'd better record the old x and the old y in x and y in a variable so that I can use it in these equations. In fact, I don't really need to record the old y, but I'll do that. Old x is x, old y is y. And then we multiply the old x and y by these constants. Right, let's see if we get a nicer looking fern now. And there it goes. I think it goes a little off the screen. It's still not working perfectly. Did I make another mistake? Let's just see the textbook. Let's just see if we have the right numbers. This stuff that we'll get to in a second is supposed to be these transformations. Let me just see if I got it right. So I can actually see here these probabilities are over there, and then I think I have another small mistake. Is it my mistake or a mistake in the book? See, this small change can actually have a big influence. So I think there's another typo in the book. Okay, right. Okay, let's see if I get a nicer picture now. This is still not the fern I want. Okay, so I fixed all the mistakes that I made before. I made some typos when I was typing in these numbers, and in addition to that, there were a couple of misprints. But for example, I had 0.750 instead of 0.075. So I fixed all of those mistakes. If we run it now, you just have to be very careful and don't doubt yourself. If there is some discrepancy between what you've got and what's in the book, it doesn't mean that you're wrong. Okay, so this time we do actually get that nice Barnsley fern. We can see this is clearly the leaf of a fern. Once again, we see a pattern emerge even though we are using a random process. These dots are natural, they're part of the picture, so they're fine. Okay, right. So the last part of the book, I'll just move this up. The last part of this section is about storing all these parameters for drawing these advanced pictures. Storing the parameters, these transformations, in a file. Instead of having to type them in, we can read them from a file. And in the case of the book, they're using standard array IO, which you can use to read a whole array, two-dimensional array, what have you, from a text file. But we know how to read numbers from a text file. We don't need that utility, and we're not going to use it. So I'm going to implement this IFS program that they have, but using my own routines to read from the text file. And let's see. What we have to start with is number of cases. So I'm going to create a new program, new class, which I'll call IFS. And I'm going to copy the code for Barnsley, but I won't need too much of it. I think I missed out a brace at the end. One more brace there. Go, right. So I'm going to stick to 500, set the dimension, set the pen radius. I'll even stick to the number of iterations, even though we could store that in the text file as well. But then I am going to open a text file. So I'm going to use in, which is part of the Princeton library, in, and new in, and the name of the text file, which the user can supply as a command line, but I'll just, for now, I'll call it barnsley.txt. So I'm hard coding the name of the text file, but ideally we want to write args0 here. Right, and from this text file I'm going to read the number of cases. So number of cases equals in.readInt. And at the same time I'm going to create the text file in another window. So I want a new folder which I'll call data inside this project, and inside here I want a new untitled text file which I'll save immediately. I can't because there's nothing in it, but there we go, now there's something in it and I can save it inside this project data, and I'm going to call it barnsley.txt. Okay. Right, so it will start with a number of cases. For Barnsley, that's 4. And then I'm going to read the probabilities. So I'm going to store the probabilities, or weights, let's call them weights. It's going to be a new array of double, if I can spell that correctly, number of cases. That's how many weights we need, and I'm going to read them. Number of cases, I++, and read them from file in. So the weight I, the ith weight, is in.readADouble. So the text file will contain those weights, and let's put them in the text file. Copy, paste them here without the commas, because we're not reading commas, we're just reading 4 doubles. And they can be in one line, that's fine, but the commas will confuse everyone. Right, so there I've read the weights. Now I need to read the transformations, and each transformation has a multiplier for the old x, multiplier for the old y, and a constant that's added. So 3 times, I need 3 arrays, and I need these 3 weights for the x transformation and 3 weights for the y transformation, and I need that for every case. So I'm going to say for int I is 0. Okay, and I also need to store these in arrays. So one array will have the factors for x, and it's going to be a new array. It has the number of cases, and y, the factor for y for each of the cases, and the factor for the constant. But this is only for transforming x. So I kind of need the same thing for transforming y. So I'm going to call these x, x, x. Those are the x factors, and these are the y factors. And I'm going to read all 6 these values from the text file almost at once, so to speak. So I'm going to say fxi is in.readDouble. And I'm going to do that for the y factor and the constant for x transformation, and the x factor, the y factor, and this constant for the y transformation. So after I read the weights, however many weights there are, I want to read, for each case, I want to read 6 doubles, and it will be these 6 doubles. That one, that one, that one for x transformation, number 4, 5, and 6 for the y transformation. So I'm going to copy all of this into my text file and take out what I don't need. Okay, so this was case 1. And as we can see here, the x factor is 0. the y factor is 0, and then I add a constant of 0.500. I want these numbers to all align, so I'm just going to pad them like this. And y, transformation is y, so it's 0 times 0, 0 times x plus 0 times 160 times the old y, and the constant is 0.000. So no constant added. That's the first case. And the next case, I'm just going to type these. There we go. So I start by saying I've got 4 cases. I give the 4 weights. Then for each of the 4 cases I have one line with 6 doubles. And the 6 doubles are the x factor, y factor and constant for the x transformation, and the x factor, y factor and constant for the y transformation. So this is a lot to take in, but I don't think it's... I know you can all do this. So right, here we read them, and then we really don't need a lot of this code down here. Now I'm still going to use a discrete selection, but I'm just going to use the weights array because that's why we read it from the file, so we can have it around. And then I'm still going to keep old x and old y. I'm not going to switch on v. V will be the index in my 6 arrays, so that let's take this one, move it up. X becomes the x factor for the x transformation, and its case number v times old x, plus the y factor for the x transformation for case v times the old y, plus x transformation constant number v. And y is almost the same. That's a y, 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 and lastly the y constant. Look how much easier this is. Okay, right. So now most of my code is concerned with actually reading the file, reading the constants from the file, and not actually the drawing part is much simpler. Let's see if it worked for Barnsley. Now this is IFS I'm running, and let's just double check. Yes, it's going to read that file. Run, and there we go. There is our fern appearing, and I'm quickly going to add the 2 other files, or at least one of the other files, and show you what that looks like. Right, so I typed the file for coral, which is an example in the textbook. Here it is. In this case there are 3 cases with their weights, and for each of the 3 cases we have the 6 transformation factors. And now I'm going to change IFS to run that. Coral, save and run, and it draws a picture of an example of how coral might grow on a reef, and it's pretty much the same as we see in the textbook. Right, if you look around on the internet you could probably find many more of these files that describe these iterated function systems. It's also used for image compression, where you take an existing image and you analyze it to see what is this little file that will generate that image. It's a lossy compression, so it's not a perfect compression of an image, but sometimes it can be very accurate and save a lot of space. Right, that's it for this lecture, and I'll see you again in class.